Separate the wave equation in two-dimensional rectangular coordinates x and y. Consider a rectangular membrane as shown rigidly attached to supports along its sides. Okay, yeah, we have to solve the wave equation, which is let's write it out. Right? You have it in your book, and it's also here. This is let me see. We're section 6, correct?
Yeah. It says problem 3, section 6.
Yeah, I know, but I'm looking for the I just want to use the same symbols they use for the wave equation, so we don't have to use different symbols. This is the wave equation. Laplacian of z equals 1 over v squared d squared z over dt squared. Okay, this is the wave equation, and we will solve this by separation of variables. Wave equation. Okay, where the xy plane is the plane we are considering, right? We know that z as a function of x, y, t is the displacement, right, of the membrane from the xy plane.
Right. I just didn't bother with z. I just put f.
Yeah, and we know from a previous section that so the way we're gonna solve this is we're gonna assume solutions of the form right. So this is x, y, and z, and you're gonna assume solutions of a certain form, differentiate, and plug back into the differential equation. So for example, here you're gonna assume what I'm saying is you assume a solution, I'll get you started, of the form. We've done a few problems, me and you, on separation of variables before. Do you remember? So yeah, so we assume, let's say here the function is z, right?
Yeah.
So you could assume solutions of the form z equal, okay, some function f of xy, right? This takes care of the spatial dependence, times some function t of time. Times some function t of time. So such that f depends on the spatial components, c carries the temporal dependence, and now you could differentiate and plug back into the equation. Good enough hint?
Okay. I think it's basically the same thing as with the heat equation.
Same exact thing. There's no difference. All these are very standard. You follow the same approach when you do separation of variables.
Except in this case, it's going to be sinusoidal.
After this, we differentiate and we plug back into the wave equation. Yeah? So let's see here. So if I differentiate this, this is gonna be del squared f times t, because that's the Laplacian. It depends on the spatial coordinates. It does not affect the time.
Right.
You understand? And so this is the this is the left hand side of the wave equation, and the right hand side. So now if I do d squared z over dt squared, now the spatial components are not affected, and you get f times d squared t over dt squared.
What was that?
And so you could multiply this side here, this second step.
This is the spatial components.
If I differentiate, okay, so here look, I have this, you understand this step here in red, where z is some product of f as a function of x comma y times t as a function of time. Yeah. And so what I do now is I need to find the Laplacian of z. Now the Laplacian has partial derivatives in x, y, and z, so that turns f into a Laplacian f, but it does not affect t. So the Laplace, so if I Laplace, quote unquote Laplace both sides here, I get Laplace on z, Laplacian on z, and Laplacian on f. T is just a number, it doesn't get affected, so it's t times Laplacian of f. And then if I go back, so now this is the left hand side of the wave equation. Now for the right hand side, I need d squared z over dt squared, so all I do is I differentiate this with respect to time. F does not depend on time, so this is just f times d squared t over dt squared. Okay, and to get it in the form 1 over v squared, I could multiply here by 1 over v squared and here by 1 over v squared, just so that I could make it exactly like the right hand side of the wave equation. Okay, and now take these and plug them into the wave equation. Enough? You can handle now?
Yeah. I think
And once I'll just write this last step, so but you could continue if you want. So if I plug them back into the wave equation, I would get t squared, t, that's the left side of the wave equation, Laplacian z, this is just t delta squared f equals 1 over v squared d squared z over dt squared. I just found it to be 1 over v squared f d squared t over dt squared. So this is so far the wave equation. Right? Okay, I'll let you continue. And here, just to make it nicer and neater, we divide by tf, which is the original z, both sides. So if I do that, the t cancels out and I get f del squared f equals 1 over v squared. Here the f cancels out and I get t 1 over f I meant, because we're dividing. So 1 over f del squared f equals 1 over v squared times 1 over t d squared t. Oh, this is small t here, dt squared. And so this is where the wave equation is so far. How are we doing, Ben? If you get stuck, let me know. And the reason I'm getting this to this form, let me tell you the main reason. Because if you look at this final equation here after I divided by tf, notice that the left hand side is only a function of f, which has in it x and y. So this is just a function of x and y, basically capital F, right? And the right hand side is only a function of t. T is a function of t. So in other words, small t is not in any term on the left hand side, and x and y are not on any term on the right hand side, and yet these two sides are equal. Now the only way that these two sides are equal is if each one of them is equal a number, because how could I differentiate with respect to x and y here, and I would differentiate with respect to t on the right hand side? No matter how I do it, those sides have to remain equal. That tells me that those terms are actually not dependent on x, y, and t. The left hand side has to be some constant, and the right hand side has to be the same exact constant. And so now that I know that this has to be a constant, and I know, like you said, since it's a wave, it has to take the equation of a wave, which means it has to have sines and cosines. I would call the left hand side k squared, but I would put a minus here, because if you have a minus and you solve this differential equation here, right, they have to be equal. So if this is minus k squared, this has to be minus k squared. And the reason I put this minus is because if you solve a second order homogeneous equation with a k squared on the right hand side, I mean, you'll see this as we do it, but you will get an exponentials, and those exponentials turn into sines and cosines, which is what's needed, because that describes the equation of a wave. If I make this plus k squared, I'm gonna get exponentials. Exponentials with real numbers do not describe the equation of a wave.
Yeah, because they don't repeat.
Right. And so that means, so what I'm saying here is, if I take the right hand side, let me work on the right hand side a little bit easier, then I have 1 over v squared f, 1 over t d squared t over dt squared equal minus k squared, right? And now multiply both sides by tv squared, so you get d squared t over dt squared equal tv squared, actually let's write it a little bit differently, minus k squared v squared times t. This is a second order homogeneous linear differential equation. You can easily write the characteristic equation of this, right? Remember the characteristic equation, r squared minus r squared equal, this is just a number here, right, minus k squared v squared, which makes r equal plus or minus kvi. And the solution for this, because you have complex numbers, are exponentials, which turn into sines and cosines. So I'll skip a few steps here. You don't have to, if you know your differential, you don't have to write them down. And so you get your t of t to be a cosine kv t, right, plus b sine kvt, which is the equation of a wave. Okay, try to get here before we continue, because you have questions so far on how I got there?
Yeah, well, with the with so where this come from?
This?
Yeah, this here.
This?
Yeah.
I differentiated both sides of this equation with respect to small t.
Okay.
This guy doesn't get affected, he remains an f.
Alright.
This becomes second derivative of t with respect to t, and the left hand side d squared z over dt squared. And then I divided both sides by z squared.
Because f doesn't have a t component. Okay.
Okay, so now let's so you solved for the t equation. Now let's solve the f equation, yeah, which depends on x and y. So I know that, so now I'm going to go to the left hand side, and I know that the left hand side will also have to equal minus k squared. Okay, so using a different color on this guy here, let's write down 1 over f del Laplacian f equals minus k squared. Okay, so that, now keep in mind, what's del squared f? That's d squared f over dx squared plus d squared f over dy squared. Okay, two variables, x and y. That's what del squared is. So now multiply the f on the right hand side. Okay, so now again we're gonna use separation of variables on this, because in this partial differential equation there's two variables, x and y. Okay, so first let me write it as delta squared f equal minus k squared f. Okay, minus k squared f. I multiplied f on there. Okay, so now this is just d squared f. So now I'll write the del for what it is, I mean the Laplacian. So d squared f over dx squared plus d squared f over dy squared equal minus k squared f. Okay, and again I will use here separation of variables. Why? Because I have two variables, x and y. So I'm gonna say assume solution. What do you think the solution here will be? Well, f will has to equal some function x of x times some function y of y. The same thing I did above, except in this case, since f is function of x and y, I just said, okay, let's say that one of those solutions is some function of x times some function of y. And we know by the completeness theorem, if I can find what this is, the linear combination of these solutions will indeed satisfy the differential equation, partial differential equation. Yeah, and then I do the same thing I did above. I differentiate this with respect to x twice, and then with respect to y, and I plug it in. So if I differentiate with respect to x twice, I get d squared f over dx squared, right, equals, now x, big X is function of x, but not y isn't. So this will be y times d squared x over dx squared. And I do the same exact thing with the y. So d squared f over d small y squared equals, now y is a function of y, but x isn't. So this will be x d squared capital Y over d small y squared. So just partial derivatives. And then, right, I would plug these into my differential equation up here. I will take these and plug them here. And so we will get, if I do that, we will get d squared f over dx squared. That would be the first one, y d squared x over dx squared, plus d squared f over dy squared will be x d squared capital Y over dy squared equal minus k squared times f. What's f? X times y. And now I divide everything by xy, just like I did. So divide by f basically, which is x times y, capital X times capital Y. And if I do that here, the y cancels out and I get 1 over x, 1 over capital X times d as a function of x times d squared x over dx squared, plus here if I divide by xy, the x cancels out and I get 1 over y d squared y over dy squared. And here if I divide by xy, they both cancel out and I get minus k squared. Now if I move one of these to the right hand side, agree, I get 1 over x function of x, this is y function of y, d squared x over dx squared equals minus 1 over y function of y, d squared y over dy squared minus k squared. Now remember, k is a number. This here is a constant. Okay? And so notice that the left hand side is only function of x and the right hand side is function of y minus some number, but that doesn't change the fact that it's a function of y. So by the same exact logic we said above, if they are equal as you are taking derivatives, they can't depend on x and y because you know, x has to be independent of y, because the minute you differentiate, they're still equal according to this differential equation. Right. And yet each one of them is a function of a different variable, therefore they have to be constants, right? So those sides have to be constants. Right. So you agree? And so we're gonna call this here kx. D squared x over dx squared to equal, so we're gonna call this constant kx squared. And is it positive or negative? Well, it has to be negative, right, to get you a wave equation.
Yeah, right.
To get the complex exponentials. Right. So if you multiply the right hand side here, so notice we're kind of repeating the same thing over and over again, yeah? So minus kx squared times xx. And now this is a second order linear homogeneous differential equation. You can find the characteristic equation, which will be the same exact characteristic equation as the one above. And skipping couple steps here, you will get x of x to be, right, sines and cosines. So let's call this c cosine kx times x plus d, because I used a and b for the one above for t, sine kx and x. Complex exponentials turn into sine and cosine. So you wanna continue there till we get to this point? Now at this point I could use my initial conditions to eliminate one of those unknown constants, because look, the question said that the rectangular membrane is rigidly attached to supports along its side, meaning when x equals 0, right,
whatever,
right, so exactly, so when x equals 0, there's not going to be any motion, yeah? And x is, remember where x is in f, So if x is 0, f is 0, and if f is 0, remember our original assumption, z would be 0. So there would be no vibration. So that means at x equals 0, I'm supposed to get x equals 0 for the z to equal 0. Right? Well, that automatically knocks what? Because if you plug it in, this is x of x. If you plug this in, you get 0 equal. Now look what's going to happen here. If you plug in 0 here, you don't get 0. You get c, because cosine 0 is 1 plus 0. Sine 0 is 0. So that means c equals 0. Bingo. So one of the initial conditions knocked this guy out. So that means I'm left with x of x equals minus kx, oh sorry, d, or let's just call it c now, since we eliminated this constant, c sine kxx.
Would this be considered a partial differential equation because there's more than...
So far we've got this, yeah?
Would this be considered a partial differential equation because there's
yeah, sure, why not?
That don't depend on each other, or there's two functions.
Well, it's partial derivative with respect to x.
Right.
Now look at the other boundary condition. Will give us the other. Notice also the same exact thing is happening at b because it's at the end. So when x equal b, I'm supposed to get no vibration. Right. Z would have to equal 0. For z to equal 0, capital X has to be 0 at x equal what was it, b or a at x equal a, along the x-axis. Right. X equal a.
Yeah. You mean, oh yeah.
Okay, so my second a at x equal a, right? Well, if the length is a, x equal a.
Oh, I thought that was...
Right? The capital X of x has to equal 0. Plug it in.
Right.
That means sine kx a equals 0. Okay? C, I could just divide both sides by c and c goes away. So look what happens here. I could determine kx. When is the sign 0? Sign is 0 when the argument inside the sign is multiple factors of pi, integer multiples of pi. So that means kxa has to equal n pi, which makes kx n pi over a, and with n equals 0, 1, 2, 3, dot, dot, dot. So we've determined kx. Fair enough? So, continue there. Questions? Yeah, the only subtlety with y here, I mean, it's the same thing. The y equation will be the same thing. The only subtlety is the fact that there's a minus sign here. So for this to work, rather than calling it like we did negative x squared for the x, you would call it ky squared for the y. You already have the minus sign in the y. You don't have the minus sign in the x. So then we can immediately go to the right, to the y and say similarly. You understand what I'm saying? This already have a minus sign here, so you're gonna say minus 1 over y d squared y over dy squared. This is function of small y. You're gonna call this ky. It has to be a constant, but rather than minus ky, it's gonna be ky, because you already have the minus sign here, which you could switch to the other side when you could multiply by minus y, so you would get d squared y over dy squared equal minus y ky. And now you can go to the characteristic equation and you will get the same solutions, right? You will get y of y equals a let's use different E and F. So E cosine KYY, right, plus F sine KYY. And let's use the boundary conditions. Again, it's fixed on the edges. So just like in the x, it was fixed at x equals 0 and y equal b, here it's fixed at y equals 0 and at y equal b. There's no vibration along the edges. So that tells us that so let's invoke boundary conditions. So that means y of 0 has to equal 0 for the f to be 0, right? For the f to be 0, and if f is 0, z is 0. Right. Okay. So, and if you plug this in here, so at y equals 0, capital Y equals 0, cosine term goes away, because you get 0 equal e plus 0, so e is 0, and this guy goes away to 0, and all we have left, the other one. Now I could use the other boundary condition. I know also at y equal b it has to be 0, there's no vibration, f equals 0, which makes z 0, and so plug this in, so you get 0 equals sine kyb, because b is y, right, along the. Okay, now we can solve for ky, because where would this be 0? This would be 0 when the argument is an integer multiple of pi, and so let's call it m here, because we used n on the first one. They don't have to be the same. Yeah, so that means b has to equal m pi over, sorry, ky I meant, has to equal m pi over b. So we've determined ky. So that means our yy is what? We used a, b, c. Let's use d here. D sine m pi over by. So that means, remember, so we've got the y and we have the x now, so we can find f, because look, the whole original assumption is f equal xy. I've determined capital X, and now I have my capital Y. So now that means f is equal to x times y. Now a constant times a constant will just be another constant, yeah, so why don't we call that constant c? Okay, sine n pi over a y x times sine m pi over by, right? But n could be anything. N could be 0, 1, 2, 3, 4, and every time you plug in a different n, you get a different sign term here. You agree? Depending where x is. And so, and then the same argument goes for m. So that means if this is a solution for n equals 0, then this would be a solution for n equal 1, should be a solution for n equal 2, which would be a solution of n equal 3, etc., etc. So that means if each one of these solutions, then the linear combination of these solutions would be a solution, and therefore I could make a sum for n, and with the same logic I can make a sum for m. So there will be a double summation here in m and n. You agree? So that means f x comma y will just equal to couple summations let's call it C and M, since we have two variables, N M sine n pi over a x, oops, the x is inside, sine m pi over by. Fair enough. So this is the f. And wait, so originally we have our t as well. Oh, so what's capital K? Remember, we already have a relationship between capital K, kx, and ky. Because look, if you go to this equation here, you're getting tired, huh? If we go to this equation here, let's call it equation 1, okay? Let's write that down. So equation 1, so let me box this first, and then we will move. Okay, equation 1. Okay, what does equation 1 tell us? Look, we call this, where is it, left hand side, we called it minus kx squared. So minus kx squared. We called the right hand, equal the right hand side, oops, we called this ky squared, and then we have minus k squared, right? Solve for k, so you get k squared equals kx squared plus ky squared, which means k is equal to the square root of kx squared plus ky squared. We don't need to determine k independently. We don't need any initial conditions on the function on the function of time, because we already know kx and ky, and they're linearly dependent. Technically, you have two unknowns here. Now the question wants you to figure out the frequency, right? So it's omega over 2 pi, right? Which is kv over 2 pi. 2 pi, yeah, 2 pi a. So okay, so let's write it out. So the frequency, right, is omega over 2 pi which would be actually, before I write the frequency, let me write the general solution first, right? The whole thing. So remember, z is equal to f times t. F as a function of x and y, and capital T as a function of small t, and I've already determined both. So let's write it out. So I could, since these are functions of m and n, I can include them in, I have to include them under the summation. So I do get, so this will be the solution for the wave equation, n m, right? F first, so c n m sine n pi over ax sine m pi over by. Okay, and then the t turned out to be, you're following, Ben? The t turned out to be a cosine kvt plus b sine kvt, but remember, I know what k is, so times a cosine k is this squared plus this squared, right? So this would be, let's leave it as k because we already wrote it here, right? Let me write it here so I don't have to write it below because it's gonna be tedious. So this is n pi over a squared plus n pi over b squared, right? Correct? Which, if you want, you could simplify it one more step. Factor, oh no, you can't, and that's fine, leave it at that. So this will be a cosine kvt, and this, let's just remove this constant and absorb it in there, yeah? So so this will be a nm plus b nm sine kvt. Okay, this would be z. Oops. Okay, and now let's go to the frequencies. So so the frequency Vmn will equal to Kmn V, right, over 2 pi yeah, okay. So let's see here. Kmn is what's Kmn? It's this is Kmn, what I wrote here in gold, yeah? This is Kmn, and so this will be k squared, so this will be n pi over a squared plus m, oops, I messed up here, this is an m, not an n. Okay, so m pi over b squared, fair enough, square root, that this whole thing is Kmn, so square root times v over 2 pi. Now notice if I if there's a pi squared and pi squared, if I factor it out, and this would be pi squared, and then pull it outside the square root, it will be pi, so it will cancel this pi that's here, yeah, and eventually I will get the final result, which is exactly what you're supposed to get to, which is v over 2 n over a squared plus m over b squared square root. This here is the characteristic frequency, and m and n are positive integers. Fair enough? It says if in case the membrane was a square, there may be degeneracy, i.e. two or more eigenfunctions corresponding to eigenvalues. Give a couple of examples here. Well, yeah, clearly. I mean, that follows from what we just got, because look, well, if this was a square, a would equal b. Okay, square. Let's finalize this before square. Then a equal b, right? And so what you're gonna get here is you're gonna get vmn will just equal v over 2, right? Now if a equal b, they'll be the same denominator here, yeah? So this will be n squared plus m squared over a squared, okay? And if you pull a out, you will get v over 2a square root n squared plus m squared. Now you will have degeneracy. Why? Because for any values n prime and m prime, you could have the same value if you swap the values of n and m. For instance, if n equal 1 and m equal 2, what would v12 be, or v21, whatever, right? It would be v over 2a, right? 4 plus 1, 5, square root 5, right? Okay, swap the values now. If m is 2 and n is 1, well, the sum will still be the same. v12 equal v over 2a square root 5. These two values are equal. v21 equal v12. So this is a degeneracy. You have the same frequency for different values of m and n, and you can come up with many examples like this. So therefore degenerate if it was a square, yeah? If a and b are different, then no. If we swap values of m and n, you understand what I'm saying?
Then it would come out to the same.
They would come out to the same frequency.
Right.
Because
this,
n squared
this
plus
would be the same thing.
Yeah.
Yeah.
So that's the idea. So that concludes this question of separation of variables, yeah? It's an interesting process and very useful. Just a few things before I wrap up this question. Notice that first a student asked me, how did we know how to get the frequency? remember this v here, this is the frequency here, this is f, Greek letter v, this is the velocity, this is the velocity. So those two v's are not the same thing. I apologize for using the same similar letters, but that's the way the book worded it. So they're two different things. We're solving for the frequency and the velocity is on the right hand side. Take a note of that. The other thing is, student asked me, how did I know how to get the frequency? Well, what's the frequency? Frequency is the omega, which is the angular speed, divided by 2 pi, and the angular speed is radians per second. So that should be calculated from the time component of the z equation. And where do I have t here? I have t, I have t here, right? This is the t term, and this here is the t term. And how do we usually find the frequency? It's whatever the coefficient of the time is, divided by 2 pi, and the coefficient of the time, I have two terms that have time in them, so I would have to take the magnitude, square the first, square the second, add them, and take the square root. And that's exactly what I did. So this, keep in mind that this here is kmn, which is capital K that we solved for here. Kmn, this is kmn, and this here is also kmn. There's 3 k's going on in this question: kx, ky, and then kmn. Kmn is dependent on kx and ky. We solved for it from equation 1 up here. And so that's how I found the frequency. I took the coefficient kmn v, which is the time coefficient in the cosine term, divided by 2 pi, and that would be the magnitude of the sum of the squares of the individual ones. And kmn, we solved for it here, so I just plugged this into the frequency equation, squared them, added them, and canceled the pi, and that's how I was able to get the frequency of the vibration of this membrane. So the x and the y terms, so I got the frequency from the time dependence, capital T of t, of the solution of z. That's it. These are the few subtleties that after I was done with this question, my students raised, and I just wanted to make that clear. Degeneracy means for different values of m and n, if this was a square and a equals b, I could swap m and n and I would get the same frequency. Again, this v here is the frequency, and the v on the right hand side again is velocity. And for swapped m and n, for any m and n, doesn't have to be 1 and 2, if you just simply swap them, you get the same frequency. I hope this is clear, and now I think we can conclude the question.